Welcome to the Depth Dive, the show where we take a look at some dense, really cutting-edge research and try to boil it down to what you really need to know.
Yeah, distill it down to the essentials.
Exactly. And today, we're tackling something that, honestly, until pretty recently, felt like a bit of a dead end in LLM architecture. Efficient linear attention.
That's right. For years, it was almost a given, wasn't it? Efficiency means you sacrifice quality. Like, that was the trade-off.
Oh, where?
But the recent release of the Kimi Linear LLM has really just flipped that whole narrative on its head.
It really seems like it.
So our mission today really is a deep technical dive. We want to get into the weeds and understand the physics of this plot twist, you can say.
Okay.
We need to dissect exactly how Kimi Linear manages to solve that historical accuracy problem, the one that plagued earlier linear methods. And we need to look at its architecture, its hybrid nature, and critically, the math behind Kimi Delta Attention, or KDA. That's the core.
Okay, let's unpack that history first, though, just to set the stage. Since the original transformer paper, the standard attention mechanism, the softmax attention, has this ON2 complexity, quadratic.
Right, and that N is the sequence length.
So as your sequence length doubles, the compute cost, the time it takes quadruples, and the memory needed also scales quadratically.
And look, this isn't just some, theoretical computer science problem. It's the central practical bottleneck, especially when you want to deploy these models, particularly at inference time.
That ON2 thing hits you twice, right? Time and memory.
Exactly. Time to compute the attention scores and memory to store that key value cache, the KV cache. That cache just balloons. If you want to handle, say, 1 million tokens of context, you need some serious hardware.
Massive. Million squared operations. Huge memory needs.
Yeah, infrastructure that can handle that kind of load is expensive and sometimes just not feasible.
So naturally, people started looking for alternatives pretty early on. Back in the early 2020s, there was a whole flurry of papers on linear attention variants. Why linear?
The promise was, well, it was simple, but potentially game-changing. Reduce both time and memory complexity from that quadratic ON2 down to linear ON.
So double the sequence length, only double the cost. Much more manageable.
Precisely. This ON scaling is what makes handling those really massive contexts, hundreds of thousands, maybe even millions of tokens actually practical, without, grinding inference to a halt or needing banks and banks of RAM.
But as we said, history wasn't kind to these early attempts. What was the big roadblock? Why did they stay mostly in research labs?
It always came down to expressivity, model quality, basically. The mathematical simplifications needed to achieve that ON complexity, they often just crippled the model's ability to capture complex relationships in the data.
Things like remembering something specific from way back in a long document, or complex reasoning.
Exactly those things. Precise memory recall, multi-step reasoning. Those suffered. So you might get a fast model, but it couldn't reliably answer tricky questions or follow complex instructions. And as a result, you never really saw a purely linear attention model become like the basis for a major open-weight state-of-the-art LLM. Until maybe now.
Right, until this recent resurgence. And 2024 has definitely seen a shift. It sort of started breaking through maybe with Minimax M1 back in June.
Yeah, that was a big signal. Minimax M1 is a huge model, 456 billion parameter mixture of experts.
MOE, right, with about 46 billion active parameters.
And they used something called lightning attention. That name itself kind of signaled, okay, efficient attention is back on the menu for serious large-scale models.
Then just a couple of months later, August, Qwen came out with Qwen 3 Next.
Right, and Qwen 3 Next also used a linear attention variant. Specifically, it looked like a variant of the gated delta net architecture, which we'll definitely get into.
Okay. And then September brought DeepSeek v3.2.
DeepSeek v3.2. They took a slightly different tack, using what they called sparse attention.
Now, sparse isn't strictly linear ON, is it?
No, not quite. It's technically subquadratic. So better than ON2, still addressing the same efficiency problem, just maybe not pure ON. But the point is, all three M1, Qwen 3 Next, DeepSeek v3.2, they showed this clear trend. The industry was really, really trying to break free from that quadratic scaling.
But then, just as things were looking up for linear attention, the plot twist. Minimax M2.
Ah, yes, the M2. The same team, Minimax, that kicked off the trend with M1, they released their next big model, a 230 billion parameter one.
Yeah.
And they went back to regular full attention. Ditch the linear stuff.
Wow. Why, did they say?
They did. They basically said that in production, linear attention was proving tricky. It seemed okay for simple prompts, maybe single-turn conversations, but they found it had poor accuracy and was fragile, especially on reasoning tasks and multi-turn dialogues.
Ouch! That sounds like the same old problem resurfacing.
Exactly. It's a huge setback for the whole linear attention idea. It really made people wonder, okay, maybe the efficiency gains just aren't worth the hit to reliability and complex reasoning. Maybe it's just not ready for prime time.
So that created this real moment of uncertainty, right? Is linear attention a dead end for production systems after all? And it's right into that uncertainty that Kimi Linear arrives.
Perfectly timed, wasn't it? Kimi Linear shows up, basically saying, hold on, we think we've cracked it.
And they came out with some pretty bold claims.
Oh yeah, not just, marginal improvements. They're claiming up to a 75% reduction in that KV cache size. Huge memory saving. And up to 6x faster decoding throughput compared to full attention.
6 times faster.
6 times, while also claiming they actually outperform full attention on quality benchmarks under fair comparisons. That's the kicker. They're saying, we're faster and we're better.
Okay, that's the claim we need to investigate. Faster and better flies in the face of the historical trade-off and the recent Minimax M2 experience.
Precisely. It suggests they've solved that core accuracy deficit while maximizing the efficiency wins.
So let's move from that historical context into Kimi Linear's actual solution. How did they do it? You mentioned a hybrid design.
Yes, it's fundamentally a hybrid strategy, very strategic. They aren't trying to make one single attention mechanism do everything, which often leads to compromises or difficult hardware optimization. Instead, they blend different types of layers.
Okay. Blending efficiency and quality. They're not throwing out the O&2 completely.
Not at all. They're using it surgically. Their approach is layer-wise hybrid. They stack different kinds of layers.
And they landed on a specific ratio, right? The 3.1 ratio.
That's the one. It's uniform throughout the model. 3 transformer blocks using their linear attention variant for every 1 block that uses a full attention mechanism.
3 linear, 1 full. 3 linear, 1 full. Repeated.
Exactly. And the thinking behind it is pretty elegant, actually. The linear layers, the ones operating at O in, they do the heavy lifting. They handle the vast majority of the processing, capturing, local context, managing the recurrent state efficiently.
And the full attention layers, the expensive ones.
They act as a kind of safety net, or maybe like a global information consolidator. They're spaced out, used sparingly, but they're there specifically to preserve that long-range global information flow across the entire sequence. And critically, they help mitigate the known limitations of purely linear recurrent structures, which can sometimes struggle with remembering very specific things over extremely long distances, that finite state capacity issue.
Right. The quadratic layers, though costly, are maybe still the best tool we have for that really deep global context integration. Okay, so what are the specific components in this blend? The linear part and the full part.
Okay, on the linear side, the star of the show is Kimi Delta Attention, KDA. This is their novel contribution, and it's described as a significant refinement of gated delta net, or GDN, the kind of mechanism used in Qwen 3 NEX.
Okay, KDA for the linear layers. What about the full attention layers? Did they just use standard softmax attention there?
Interestingly, no. That's another key design choice. They replaced standard full attention with something called Multi-Head Latent Attention, or MLA.
MLA. Okay, wait. If the goal is overall efficiency, why introduce another non-standard component like latent attention? What is MLA, and why pick that over just regular, well-understood full attention?
Good question. MLA, multi-head latent attention, is essentially a way to make full quadratic attention cheaper, computationally speaking. Standard attention computes similarity between all pairs of tokens in the sequence. If you have T tokens, that's a T by T matrix. Very expensive.
Right, that's the ON2 part.
MLA introduces a bottleneck. It projects the key and value matrices down to a much smaller, fixed-size latent space before doing the big matrix multiply. Let's say the sequence length T is huge, like 1,000,000, but the latent dimension dollars is small, maybe 128 or 256.
Ah, okay. So the attention calculation itself still considers all token positions, making it full attention, but the actual matrix multiplications happen in this much smaller latent space.
Exactly. It's still technically O(n)(2) with respect to the sequence length n because you still process all inputs, but the constant factor in front of that n2 is dramatically reduced because the core computation involves these smaller latent matrices.
So it's a way to get the global reach of full attention, but at a significantly lower computational cost compared to standard softmax attention.
Precisely. Kimi chose MLA because it provides a big efficiency boost for those necessary quadratic layers without completely sacrificing the global view that they need to maintain coherence and performance. So they optimize both sides of the hybrid equation.
Right. It wasn't just, let's improve the linear part. They improved the linear part with KDA, and they made the full attention part cheaper with MLA.
A two-pronged optimization.
Which brings us back to those eye-popping efficiency metrics they claimed. That 75% KV cache reduction and the 6x throughput, these are tied to the architecture.
Absolutely. The 75% KV cache reduction is huge for inference. Remember, often it's not the raw compute FLOPs that limits you during inference, it's memory bandwidth and capacity. How fast can you read and write that huge KV cache?
And how much VRAM do you need just to hold it?
Exactly. Cutting that memory footprint by 75%. That fundamentally changes the hardware requirements, makes deploying these giant models much cheaper, much more accessible.
And the speed, that 6x decoding throughput for 1 million tokens, that's not just incremental.
No, it's transformative for certain applications. Think about AI agents that need to generate long plans or reasoning chains, or high-throughput services generating lots of text. A 6x speedup means your agent can think 6 times faster, where your service costs drop dramatically.
But the crucial part, the part that directly challenges that Minimax M2 finding, is the performance claim. They're saying Kimi Linear, this hybrid model, is actually better than a baseline using just the full MLA attention.
Yes, and they show this across the board. Short context benchmarks, long context benchmarks, and even in challenging reinforcement learning scaling scenarios. This is the core claim. Linear attention, when done right with KDA, isn't just a replacement. It's an upgrade in both performance and efficiency.
Okay. This implies the KDA mechanism itself must be significantly more expressive or capable than previous linear attempts, like the one Minimax M2 struggled with. It has to handle that complex reasoning.
It must. And that means we need to dive into the technical core of KDA. How does it work mathematically? Why is it better?
Let's do it. Trace the lineage for us. How did we get from basic linear attention to KDA?
Okay, so the early, simple linear attention models, they essentially acted like an online learning system, maintaining a state, let's call it CC-day. This state was like an associative memory, and it just accumulated key value associations over time. The update was simple, CCT, ST1, plus KTVT.
So at each step T, you just add the outer product of the current key and value to the memory state from the previous step.
Right. Simple, but fatally flawed. It suffered from catastrophic interference.
Meaning
Meaning the state just grows and grows, unbounded. It never forgets anything. So when a new query teller dollar comes along trying to retrieve relevant information, it interacts not just with the specific past memories it needs, but with this massive noisy aggregate of every single key value pair the model has ever seen.
Like trying to find a needle in an ever-growing haystack, the signal gets drowned out by the noise of everything else.
Exactly. You lose selective recall. So to fix this, DeltaNet came along. DeltaNet had a clever idea. Reinterpret this recurrence not just as accumulation, but as online gradient descent.
Online gradient descent. On what?
On a reconstruction objective.
Yeah.
The goal became to train the state zeros so that, given a key seriate dollars, it could accurately reconstruct the corresponding value VT2. The loss was something like LTS Fairway stop years. Minimizing this loss leads to the classical delta rule update.
And that update looks different.
It does. It involves a corrective term, Siritup, SS speedup, ST1 plus beta KT CT Tatari. Here, PATIS is like a learning rate. You subtract a rank 1 matrix related to the current key from the identity before applying it to the old state, and then you add the new key value information. It's trying to correct the state based on the current error.
Okay, that seems more stable. It's adjusting based on prediction error, not just blindly adding. But does it explicitly forget? It still carries forward the modified zero node?
Not explicitly, no. That was the next step. Gated DeltaNet, or GDN. GDN introduced an explicit forget mechanism, a simple one, but important. It added a scalar forget gate, let's call it alpha dollar, a value between 0 and 1.
A single number controlling forgetting.
Right. It acts like weight decay on the memory. The GDN recurrence became at a delta at DT top ST1 plus beta KTVT top. That scalar alpha just multiplies the entire previous state after the delta correction before adding the new info. If an alpha is close to 0, it forgets quickly. If close to 1, it remembers longer.
GDN was used in Quen 3 next, or a variant of it, so that was a big step. But Kimi saw a limitation even here.
They saw a key limitation. That single scalar gate, alpha dollar. Think about it. The memory state dollar is a matrix, maybe encoding hundreds or thousands of different features in its dimensions. dk times dVA.
Right. Different parts of the memory might represent different kinds of information.
Exactly. Some dimensions might track syntactic structure, others semantic concepts, others may be positional information implicitly. That single scalar alpha dollar forces every single one of those features, every dimension, to decay, to be forgotten at the exact same rate.
Ah, I see. That's very coarse control. You might want to remember the main topic of a document for a long time, but forget the specific phrasing of the previous sentence much faster. A single gate can't do that.
Precisely. It drastically limits the model's expressivity and its ability to manage memory effectively for complex tasks. And that is the core technical insight of Kimi Delta Attention, KDA.
They made the forgetting mechanism more granular.
Much more granular. They replaced that single scalar gate alpha with a channel-wise diagonalized gate, written as text diag. Here, alpha isn't a scalar anymore. It's a vector with a separate decay value for each of the key dimensions.
Wow. So every feature channel gets its own independent forget rate?
Exactly. Fine-grained gating. Let's look at the KDA recurrence equation there, equation 1. Text, K base I, plus beta du top. See where text d die cap. See where text diet fits. It multiplies the previous state st1 before the corrective delta update. This diagonal matrix applies a different multiplicative decay factor from the vector alpha to each row or channel of CT-tall.
Okay, so the model can now learn, for instance, feature channel 5 needs long-term memory, keep its decay rate near 1. Feature channel 87 captures fleeting details, decay it rapidly towards 0.
That's exactly the idea. This selective memory regulation, this ability to precisely control the lifespan of different learned features, that's what they argue unlocks the superior accuracy, especially on tasks requiring both long-term memory and sensitivity to recent context. This is likely how they overcame the reasoning limitations that Minimax M2 encountered.
That makes intuitive sense. But adding a whole vector gate, elevelton instead of a scalar, doesn't that add a lot more parameters? Doesn't it make the computation more complex and potentially slower, undermining the ON benefit?
That's the critical trade-off, and you've hit on the next piece of the puzzle. Hardware efficiency. Yes, generating that dimensional gate vector alpha dual requires more parameters than generating a scalar. But the expressivity gain seems to be worth it. The real challenge was making this mathematically more complex recurrence run fast on GPUs.
Right. Theoretical ON is nice, but if the constant factor is huge because the calculation is messy, it might still be slow in practice.
Exactly. And this brings us to the DPLR problem, diagonal plus low rank matrices. The kind of state transition needed for KDA, involving that A to K tech top dollar and the diagonal gating, falls into this general DPLR structure. $dollars at DTech dollar.
And you're saying general DPLR structures are hard to compute efficiently.
Notoriously hard to parallelize well. They often involve steps that break the nice, smooth data flow GPUs love. Previous attempts at fancier recurrent updates often stumbled here. They looked good on paper, but had slow kernels.
So how did KDA solve this? They didn't use a general DPLR.
They used a constrained DPLR variant. This is maybe the most clever hardware-aware part. They noticed that if they bind the A and B vectors in the general DPLR form back to the key vector and gate vector alpha doll in a specific way, A to key tech take A8 and the A to O is element-wise multiplication, the whole structure becomes consistent with the math of the classical delta rule update.
Okay, so tying it back to the delta rule structure helped.
That specific mathematical structure, that constraint, allowed them to design a bespoke, highly optimized, chunk-wise parallel algorithm for computing the KDA recurrence.
Chunk-wise parallel, meaning they process the sequence in chunks.
Yes, but in a very optimized way. Without getting too deep into the weeds, the general DPLR update might require, say, 4 separate matrix calculations within each chunk processing step. By using their constrained formulation, they reduced that number to just 2. They eliminated 3 extra matrix multiplications that would have been computationally expensive and required more synchronization.
And the result?
The result, according to their paper, Figure 2, was a kernel efficiency improvement of roughly 100%, basically a 2x speedup, compared to implementing the same fine-grained gating using a more general DPLR kernel, at least for sequences up to 64K tokens.
Wow. So they made the math more complex, fine-grained gating, but then found a specific formulation and algorithm that allowed them to compute that complex math twice as fast as a naive implementation.
Exactly. That 2x kernel speedup is crucial. It effectively paid for the extra complexity of the fine-grained gating, allowing KDA to be both highly expressive and very fast, maintaining competitive speed with simpler OLEN methods like the baseline GDN.
They got their cake and ate it too. Expressivity and speed.
Seems like it. They also mention optimizing the output calculation using an interblock recurrent and interblock parallel strategy. Basically, process everything within a chunk in parallel, pass the state recurrently between chunks, maximize GPU utilization.
Okay, that KDA deep dive was fantastic. It really connects the math to the performance claims. Let's zoom back out a bit. We know the KDA kernel is special. How are the inputs to KDA, the queries, keys, values, and that gate vector alpha actually generated by the network layer?
Right, the neural parameterization is quite specific. For the query colors, key dollars, and value dollar inputs, they first pass the input embeddings through a shortconv layer.
Shortconv, like a small 1D convolution.
Yeah, typically a very small kernel, like maybe 3 or 5 taps. It helps capture very local dependencies, kind of like a learned positional bias for the immediate neighborhood, before feeding into the main recurrence. After shortconv, they use a swish activation function.
Okay. Anything else notable about Q and K?
Yes, very important for stability. Both 2,000 and dollars are normalized using L2 norm.
Why L2 normalization?
In these deep recurrent systems, especially when dealing with potentially long sequences, you can run into issues with exploding or vanishing activations or gradients. Normalizing the vectors involved in the core recurrence, like Tor and dollars, helps keep their magnitudes controlled, which in turn helps stabilize the eigenvalues of the implicit state transition matrices. It's crucial for successful training.
Got it. Stability measure. Now, what about that all-important per-channel decay gate vector, alpha dollars? How is that generated?
Alpha dollar is generated using a low-rank projection from the input embedding, followed by some decay function, score into a dollar, which likely maps the projected values into the desired 0-1 range, maybe using a sigmoid or a variant. Using a low-rank projection here helps keep the parameter count for generating the gate manageable.
And there's one more gate, right? An output gate.
Yes. After the KDA computation produces the output Ontario, they apply another data-dependent gate. This one uses a sigmoid function, again parameterized via a low-rank projection.
Sigmoid specifically, did they test other options?
They did. Their ablation studies, Table 7 in the appendix, I think, showed that using this sigmoid output gate significantly outperformed alternatives, like using swish activation for gating, or having no output gate at all.
Why would sigmoid work so much better there?
The sigmoid function squashes its output strictly between 0 and 1. This provides a very smooth, controlled way to modulate the final output based on the input context. It might help the model learn to selectively pass through or suppress information from the KDA layer in a stable manner, which seems critical for performance.
Okay, so lots of careful engineering in the parameterization. Shortconv, L2 norm, low-rank gates, specific activations like swish and sigmoid. It all adds up. Now, speaking of architectural choices, there's another really interesting one, the no PE strategy.
Yes, no position encoding. Specifically, they apply no PE to all the full attention layers, the MLA layers.
No positional encoding on the quadratic layers. That seems counterintuitive. Don't those layers need position info to handle the global context?
That's what makes it a fascinating choice. It's a deliberate delegation of responsibility. By removing explicit positional encoding, like ROPE, rotary positional encoding, which is common, from the MLA layers, they're essentially forcing the entire burden of encoding positional information and understanding sequence order onto the KDA layers.
So the linear KDA layers are now responsible for both the recurrent memory and understanding position.
Exactly. The KDA layers have to figure out where things are in the sequence implicitly through their learned recurrent dynamics.
Why would they do that? ROPE works pretty well, doesn't it? It's been the standard for many top models.
ROPE does work well, especially within the context lengths it was trained on, but it has known issues with the extrapolation. ROPE uses fixed trigonometric functions to encode position. If you train a model with ROPE on, say, 4,000 tokens, and then try to use it at inference time on 100,000 tokens, those fixed frequencies might not generalize well to the much longer distances. Performance can degrade.
Ah, the extrapolation problem. And the idea is that KDA might be better at this.
That seems to be the hypothesis. In the paper, Table 6, they frame KDA itself as a form of learnable multiplicative positional encoding. Unlike ROPE's fixed rotation matrices, KDA's state transition, the way information propagates from step $t to $2, is data-dependent. It's learned based on the actual input features.
So the positional signal in KDA isn't fixed. It adapts based on the context.
Right. The recurrence itself learns how to track position and recency as needed for the task, potentially making it more robust when generalizing to sequence lengths much longer than seen during training. By using no PE on the MLA layers, they ensure that this adaptive, learned positional awareness from KDA is the dominant mechanism throughout the network.
That's a really clever way to potentially solve Ropey's extrapolation issues and boost long context performance by leaning entirely on the recurrent dynamics of KDA.
It seems like a key part of their strategy for achieving those strong, long context results. It makes KDA do double duty: efficient attention and adaptive positional encoding.
Okay, let's circle back one more time to that 3.1 ratio. It felt empirically derived, but did the ablation study give any more insight into why 3.1 was the sweet spot?
The ablation study, Table 1, was pretty clear. They tested various KDA MLA ratios, pure MLA, 1.1, 1.1, 3.1, 7.1, even 15.1.
And 3.11.
It yielded the lowest validation perplexity, which is a good measure of how well the model generalizes to unseen data. It hit 5.65 perplexity. Ratios with even more linear layers, like 7.1 or 15.1, were maybe slightly faster theoretically, but their validation perplexity was significantly worse, even if their training loss was comparable.
What does that suggest? Worse validation perplexity despite similar training loss.
It strongly suggests overfitting or poor generalization. The models with very few full attention layers, 7.1, 15.1, might have learned the training data well, but they couldn't generalize that knowledge effectively. They likely lost too much global context information without enough MLA layers to anchor them.
And pure MLA, 0.1.
That also performed poorly compared to the hybrid models, validating the need for the efficient linear component. So the 3.1 ratio wasn't just random, it emerged as the optimal engineering trade-off. It's the minimum amount of expensive global attention needed to ensure the model generalizes well, allowing the efficient KDA layers to handle the rest.
The Goldilocks ratio, found through careful testing. Not too much MLA, not too little.
Exactly. It's the balance point for quality and throughput.
All right, so the architecture seems incredibly well thought out. Expressive KDA kernel, hardware optimized implementation, lightweight MLA for global context, no PE delegation, and that empirically validated 3.1 ratio. Now let's get to the proof. The performance results. Did it actually deliver?
The paper presents a pretty comprehensive set of results, aiming squarely at proving KDA overcomes the historical weaknesses. Let's start with standard short context tasks after pre-training on 1.4 trillion tokens.
How did Kimi Linear stack up against the baselines, the pure MLA model, and also GDNH, which is like the Qwen 3 Next style hybrid?
Kimi Linear consistently came out on top. If you look at Table 3, on general knowledge benchmarks like MMLU Pro and BBH, and reasoning like GSM-8K, Kimi Linear scored highest after pre-training.
Can you give an example? Like MLU Pro?
Sure. MLU Pro pre-trained score, Kimi Linear got 51.0, the MLA baseline was 47.2, and GDNH was 47.9. So a noticeable jump for Kimi Linear.
Okay, and this pattern held after fine-tuning as well.
Yes. Table 4 shows the results after supervised fine-tuning, SFT. Kimi Linear maintained its lead, especially on the harder reasoning and math tasks. For example, on AMY 2025, a challenging math benchmark, Kimi Linear SFT scored 62.1, whereas the MLA baseline got 57.1.
That directly addresses the Minimax M2 concern, right? They struggled with reasoning, but Kimi Linear seems to excel there.
It absolutely does. The fine-grained gating in KDA seems crucial for retaining the precision needed for these complex multi-step tasks. That ability to selectively manage memory is key.
Okay, strong results on short context, but the main motivation for linear attention is long context. How did it do there? They tested up to 128K.
Yes. Table 5 shows the long context evaluations at 128,000 tokens. Kimi Linear again achieved the highest average score across various tasks, hitting 54.5 overall.
Any specific standouts?
It did particularly well on Ruler, scoring 84.3, which is designed specifically to test the effective context length the model can handle, and also Repo QA, 68.5, which involves understanding long code repositories. Importantly, even the GDNH hybrid baseline showed some degradation relative to the MLA baseline on certain long context tasks. But Kimi Linear consistently performed at the top, suggesting KDA itself is very robust at length.
And what about reinforcement learning? That's often sensitive to architectural choices.
Figure 6 shows RL performance during math training. Kimi Linear not only started from a better point due to better pre-training SFT, but it also showed a superior scaling trend during RL. It learned faster and reached higher scores on test sets like Math 500 and AIM 2025 compared to the MLA baseline, using the same amount of RL training compute. Faster learning, better final performance.
So across pre-training, SFT, short context, long context, and RL scaling, Kimi Linear consistently outperforms the MLA baseline and the GDN hybrid.
That's the picture the results paint. Performance superiority alongside the efficiency gains.
Let's quickly recap those efficiency gains in terms of complexity. We know the inference speedup comes from the KV cache reduction. What about training complexity?
Right, the FLOP's comparison. Full attention, as we said, is quadratic in sequence length T, text at Batiste, approx 2K2 DHD. That 2D22 term dominates training costs for long sequences.
And KDA.
KDA is linear in T. The formula is a bit more complex because it depends on the chunk size C and head dimension DACDH, 6TDH2 plus 3TCDH plus TC22. The key is that all terms are proportional to $2, not T2.
So theoretically, linear scaling for training FLOPs, did they quantify the practical training efficiency gain?
They did. Figure 5 shows scaling law plots. They estimate that Kimi Linear achieves roughly 1.16 times better computational efficiency during compute-optimal training compared to the MLA baseline.
So for the same training budget, you could train a Kimi Linear model roughly 1.16x larger, or train it for longer, leading to a better final model.
That's the implication, better scaling loss.
Okay, so we have theoretical FLOP's advantage leading to better training scaling and massive inference speedup up to 6x, driven by the huge KV cache reduction allowing larger batch sizes.
Exactly. The inference speedup is primarily an I/O and memory advantage. KDA's recurrent state is fixed size, dk times dvy through head, completely independent of sequence length T. You eliminate that massive KV cache that grows linearly with T. The memory saved can be used to pack more sequences into each batch on the GPU, dramatically increasing throughput.
That makes sense. The memory saved gets reinvested into parallelism via batching.
That's the key to the 6x number at million token scale.
Right, let's try to wrap this up. Zooming out, what's the big picture takeaway from Kimi Linear?
I think the story is that Kimi Linear successfully tackled and, based on their results, largely mitigated the primary historical weakness of linear attention, that accuracy degradation, while fully leveraging its core strength, the ON efficiency.
It seems like they've broken the long-standing trade-off, showing you can have both speed and quality, at least with a specific architecture.
It really feels like a critical milestone. It counters the narrative setback from Minimax M2 and strongly suggests that linear attention, when implemented with sophisticated mechanisms like KDA's fine-grained memory control, isn't just a research curiosity. It's a viable, high-performance, production-ready approach.
So the standard for hybrid models has been raised. It's not enough to just mix linear and full attention. The quality of that linear component, like KDA, is now paramount.
Absolutely. Kimi Linear establishes a new kind of performance hierarchy. This specific combination, the sophisticated channel-wise gated delta rule, KDA, paired strategically with the 3.1 no-P MLA hybrid structure, seems to be the most effective architecture found so far for balancing performance across everything. Short context, long context reasoning, and getting massive efficiency gains.
It's a really smart division of labor within the model architecture. Delegate local processing and sequence modeling to the efficient KDA layers. Use the sparse MLA layers for global grounding and stability.
Yeah, and KDA is doing double duty handling positional information too.
Right, which leads us perfectly into the final provocative thought for you, the listener, to chew on.
We've seen how KDA, with its learned data-dependent transitions, effectively takes over the role of positional encoding from fixed methods like ROP, especially when combined with the no-P strategy.
And it seems to do it more robustly, especially for extrapolation.
So here's the question. If these learned context-sensitive dynamics prove consistently better at handling positional awareness and generalizing to unseen sequence lengths than fixed mathematical constructs like ROP, does the future of efficient long-context LLMs lie in fully delegating both attention and positional encoding to these complex but ultimately highly efficient and adaptive recurrent memory mechanisms like KDA?
Are we heading towards models where the recurrence is the attention and the position encoder all rolled into one optimized kernel, getting rid of separate fixed positional embeddings altogether?
It's a fascinating possibility. Could models that learn sequence structure and position dynamically from the data itself be inherently more scalable and robust than those relying on fixed, predefined structures? It challenges some long-held assumptions.
A future where the architecture adapts more fluidly, that would be a paradigm shift, something for us all to watch.
Definitely. We'll be keeping a close eye on all the architectures that inevitably follow Kimi Linear's lead in this revitalized quest for ON state-of-the-art performance.
Well, thank you for joining us on the deep dive into Kimi Linear. We hope this technical breakdown has helped clarify why, after years of seeming like a dead end, ON efficiency is suddenly very much back in the running for building the next generation of powerful and practical large language models.